So both types 1 and 2 carbonyl compounds are weakly basic. By weakly basic, meaning that they will not react readily with acids unless you have strong acids. At the carbonyl oxygen, and like I said, are protonated by strong acids. So suppose we have so once again, it's essential that you remember that the protonation occurs at the carbonyl oxygen, this one right there. So if we have an acid, then again, a proton is attacked by the lone pair on the carbonyl oxygen. And you end up actually with some resonance structures. But first, let's actually draw this. So you have oxygen now with 3 bonds, which means it's positive, has a formal charge of positive. It's not happy. But it can be resonance stabilized by remembering some resonance. So we can take the lone pair from the oxygen, the other oxygen, and now the positive is on this one. So this is resonance stabilized, Conjugate, of course, this is a conjugate acid. Conjugate because this one acted as a base. Base, remember, attacks a proton. Protonation of the carbonyl compounds greatly enhances the electrophilicity of the carbonyl carbon. Acid catalysis is often used to enhance the electrophilicity of the carbonyl carbon so that it's more easily attacked by weak nucleophiles. So what it does is this step in the middle, we probably didn't show it, but we'll show it right here. A step in the middle will basically look like this. Where you have a positive charge on the carbonyl. So this is highly electrophilic. Which again makes it prone to an attack by even weak nucleophiles because of this positive charge on the carbonyl carbon. Now, this is very important. I asked this question when I was an undergrad. Why does the protonation occur at the carbonyl oxygen? Why not the carboxylate oxygen, the other oxygen? Well, let's look at it. So we would rather understand than just memorize. So this is the one we drew before. If the carbonyl oxygen attacks, And we said that this is resonance stabilized. We agree that this is resonance stabilized conjugate acid. Just basically what we talked about here. It's resonance stabilized. However, what if the protonation occurs at this? So imagine if we didn't react it with this one. Let's say we reacted it this way. This lone pair on the carboxylate oxygen attacked the proton. Okay, so let's draw the result of that down here. So that would be the carbonyl is untouched. But then you would have the carboxylate oxygen with the 2 hydrogens. We added another one. And of course, it would have a positive charge on it. So you might be saying, okay, well, we can stabilize it. We have that lone pair, and we can use that lone pair to do to draw other resonance structures. Well, let's do that. So we move that there, and then we move that here. You'll see a big problem arising here. Let me just... Okay, we have a huge problem here. We have a huge problem. And the huge problem is that this oxygen has 4 bonds. Okay, you will never in organic chemistry see oxygen with 4 bonds because this will end up with a positive 2 charge if you calculate the formal charge. Oxygen is the second most electronegative atom, so it can't, having 1 positive is bad. Having 2 is just very, very bad, okay, even worse. Simply because, again, it's a very electronegative atom. It can attract electron density, not lose electron density or share too many. So this would be a positive 2 charge. So this is not plausible. So this one, therefore, is not resonance stabilized. So we can ignore this one. As far as the carbonyl compounds, types 1 and 2 being acidic, we would have to draw this and show you. So imagine you have an aldehyde, and we would like to take a look at the methyl that's attached here. Of course, it could be an alkyl group, but we're drawing a methyl. So we call this carbon, and we will study it extensively in chapter 23. We call this an alpha carbon. So if we have a base to attack this, it's possible because it's acidic relatively. And the reason why is because the pKa of this carbon right here is around 20. And one of the reasons why that's possible is because of resonance. It's once again resonance stabilized. So if we have now H2C, we can shift these here. right there. So once again, these are resonance stabilized, what we call them, we have a name for them, call them enolate ions. It is very, so we'll study this in chapter 23 and 24. It is very, very critical that you get very comfortable with drawing resonance structures for carbonyl compounds. So you should be able to do this very, very quickly. You know that resonance structures are going to involve this carbonyl bond. So you'd have to move the pi bonds onto the oxygen, and then, of course, move whatever other delocalized electrons to replace that pi bond. So be accustomed to this because, like I said, it's very, very critical.